Graphing motion at a constant acceleration. In physics, there's another approach in addition to algebraic, which is called graphical analysis. The kinematic Formula 1, which is final speed equals initial speed plus the product of acceleration and time, can be interpreted by the graph. We just need to recall our memory from our math classes where we already saw a similar formula, y equals mx plus b. So final speed is to y, initial speed is to b, m is to acceleration, and t is to time. So these are analogous, and if we looked at the velocity graph for an object experiencing a constant acceleration, we'd see that they're both linear equations. So if we start off with some acceleration, as time goes by, our velocity goes up, positive acceleration that is, and we get a straight line relationship. Now keep in mind, let's just write quickly on the board. The starting speed is down here. The ending speed would be up there. That's the final speed. A little stray dot there. And the acceleration would be the rise over the run. We know that y equals mx plus, there we go, b. And we know that the y value, the final speed, which is the final y value, we'll call that v, is equal to the slope of this, which is the rise over the run, the delta v per delta t, which is the acceleration, times the x variable, the time, plus the initial speed. This isn't very familiar the way it's written, so let's just rewrite it. The final speed is the initial speed plus the acceleration times the time. So interesting. This graph gives birth, if you will, to our how fast equation number 1. Not only do graphs give us equations, but graphs have incredible amounts of information hidden in them that we'll address within this course. So these graphs are storytellers. Once again, as we stated in the previous slide, the slope is the rise over the run, and the slope of the velocity time graph is the acceleration. And from that we can get tremendous information, so we can interpret this. The question is, the velocity as a function of time is presented by the graph. What is the acceleration? Let's just take a peek. What is the starting speed? What is the speed at t equals 0 seconds? The way we do this is to draw a line up until we, there's the speed. We start off with positive 2 meters per second of velocity. I should say velocity, not speed, but we use those terms interchangeably. As time goes by, tick, 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 time is ticking. Sometime later, 40 seconds later, we have a new velocity. Our new velocity at that point is equal to positive 10 meters per second. Now, as time progresses, tick, 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 there is a delta v, and the acceleration is in the positive direction. Delta v is in the positive direction. We know that the time, the elapsed time for this journey that we specified, you could pick any 2 points, it wouldn't make a difference, is from 0 seconds to 40. So that would have been a total of 40 seconds. And the question is, what is the acceleration? We don't know that. That's in meters per second squared. We know acceleration is delta v per delta t. So we can say delta v is v minus v naught divided by t. Now I'm going to sub in the numbers because I'm running out of room. The final speed was 10 meters per second minus the initial speed of 2 meters per second divided by a total of 40 seconds. So this will give us a delta V of positive 8 meters per second and a delta T of 40 seconds. So we can find the acceleration. It's a fraction of a meter per second squared. Let's reveal the answer. 0.2 meters per second squared. Graphs are storytellers. They're very informative. From this graph we could find out starting, ending speeds. We could find the speeds at any point in the times that are provided. We may even choose to go beyond, extrapolate if we had to. If we knew the acceleration was going to remain constant, we could tell what the speed was going to be beyond that. Or we could find the slope and then predict the speeds at any points and any times. So beautiful.